Okay, so if you don't understand the basic concept of the types of data and then what specific hypothesis that you have to run and then normality test that you have to run, you will not be able to do any parametric tests in your exam. And it's very simple. I promise you, it's very, very simple. So let's begin. Now, generally speaking, there are generally speaking, there are two types of data. So there are the categorical data and then the numerical data. What do we mean by categorical data? Categorical data are the types of data that are in groups. And then the numerical data are those that are what? Figures.
Yes. I'm joining you. Why are you going out? Oh.
So there are two types of data. The first is the categorical data, and then the next is the numerical data. So please, I'm muting everybody. I'm muting everybody so that if you have anything, just type it in the chat so that we don't have any distractions. Good. So the purpose of data collection is to obtain information about an area of research. Each data collected has different characteristics. Each data collected has different characteristics, and these characteristics are called variables. These characteristics are called variables. Okay, so an example would be gender, age, height, and so on and so forth. Okay, so as I mentioned earlier, we have categorical data and then numerical data. Now, categorical data are qualitative, and then numerical data are quantitative. What do I mean when I say qualitative and quantitative? When I say quantitative data, they are the types of data that you can be able to measure, like how many something is or how much something is. So numerical data is measurable, but the categorical data are not measurable. Okay, moving on. Categorical data can be grouped into two groups. We have the nominal and then the ordinal data. The nominal and then ordinal data. The nominal data is a type of categorical data that is in no particular order. It's in no particular order. For example, gender, that is male or female. Blood type or blood group, that is AB, AB negative, A, B, and so on and so forth. Then we have other examples like two binary variables like present or absent, yes or no, and so on and so forth. Now, so that is for nominal categorical data. So the nominal data are types of categorical data that are in no particular order. Then we have the ordinal data. The ordinal data are the types of data that are in a particular order. The ordinal data are the types of data that are in a particular order. For example, disease staging, like severe, disease staging, like stage 1, cancer type, stage 2, stage 3, stage 4. These are ordinal types of data. And then we have degree of pain. Degree of pain. So the degree of pain, you can have maybe moderate, severe, and low. So these are the two types of categorical data. You have the nominal, which is in no order, for example, gender, and then the ordinal data, which is in a particular order, for example, degree of pain or education level. Then we have the numerical data. The numerical data. Now, the numerical data, remember I said these are the what? Quantitative types of data, right? Good. So they can also be branched into two groups. The first is the discrete data, and then the second is the continuous data. What do I mean when I say discrete data or variables? Now, the discrete data or variables are variables that take whole number forms. For example, 1, 2, 3, 4, or number of visits to a hospital. For example, I say, how many times did Efia Boatima visit the hospital today? Then the answer will be 6 times. Or how many times did Abel visit church the whole year? Then you say maybe 200 times. So that is discrete data. Another type of data that we have is continuous data. Continuous data. Now, the continuous data is a type of data that are in a range of values, and they include even decimals. So, for example, 0.01, 0.001, 0.2, 0.3 is 1.4, 14.6. All those ones are continuous variables. Continuous variables. So what are some examples of continuous variables that we have? We have weight, we have height, and so on and so forth. We also have BMI, but just to mention a few. Okay. So these are the two main types of data we have. Please, I hope everybody understands. Categorical and then numerical. Good. Please note, in SPSS, if you are inputting a data and then you miss, maybe, for example, you miss a data here, assuming I was entering in shoe sizes and then I don't enter the shoe size for number 16. If I don't input the shoe size for number 16, let me look for shoe size. Good. If I don't input the shoe size for number 15, you see there's nothing there, it's blank. So all missing variables like these are represented by a full stop. In some applications, it will be represented by an asterisk. In other ones, it will be represented by 99 or minus 99 or 999. So anytime you see a full stop or asterisk or minus 99 or minus 999 or something like that, then you know that you have some missing data in the variables. But SPSS will label it as missing data so that you'll be able to know that it is a missing data. Okay. So, degree of pain. We said degree of pain is an example of what? The categorical variable that is under the ordinal variable, right? Now, degree of pain can't actually be measured. For example, if I should pinch you right now, and then I ask you that, is it painful? all you can say is maybe yes, it's painful, or it's very painful, or it's not painful at all, or it's moderate, or whatever, right? But in data, when you are trying to analyze something like that, we would have to assign a value to it. So what we do is that we assign a score to it. For example, you go to somebody and then you hit the person, and then you tell the person that from a range of 1 to 10, how will you describe your pain? Then the person can say, oh, maybe 6.5. Another example is maybe beauty or taste. You say from a range of 1 to 10, how beautiful is so so and so? Then the person will be like, oh, it's a 10 over 10, or it's a 0 over 10, or it's a 5 over 10. So for categorical variables like that, we assign scores to it. Good. Moving on. Other categorical variables are represented by frequency distributions. Now, this categorical variable and then this numerical variable can be represented in SPSS with a pie chart, a mosaic plot, or a bar chart. Let me come again. Categorical variables in SPSS, for example, blood group, maybe gender, degree of pain, education level. All these are categorical variables. If you want to represent them in SPSS statistically, then you have to use either a bar chart, a pie chart, or mosaic plot, and so on and so forth. For continuous variables, so moving on, continuous variables, for example, weight, height, age, number of visits to a hospital, all these continuous variables are represented in SPSS with dot plot, scatter plot, stem and leaf plot, histogram, heat maps, and so on and so forth. But the common ones will be the dot plot, the scatter plot, stem and leaf plot, and histogram. So let me come again. Categorical variables are represented by frequency distributions, including pie charts, bar charts, and mosaic plots. However, continuous variables are represented by dot plots, scatter plots, stem and leaf plots, histograms, or heat maps. Now, anytime you draw a map on SPSS, when you are doing an analysis and you get a range of values or a range of figures. Now, figures or variables or observations that are distinct from the main body are called outliers. So, for example, maybe you have a range of weights, body weights. Everybody is maybe from 30 to 60 kg, but some few groups of people are overweight and their weight is let's say 100 kg or 200 kg. So those people whose weight differs significantly from the rest of the population are called outliers. Outliers. I hope everybody understands. Let me quickly check the charts. See. Okay. think there are no questions, so we can continue. So moving on. So now that we understand the difference between the types of data sets we can have in SPSS, now we can test if the data set is normally distributed in the population or is not normally distributed in the population. What do I mean by testing if the data set is normally distributed in the population or not? When we say a data set is normally distributed in the population, it means that the results from the data set can be applied to real life situations, meaning that the data set has an effect on real life situations. Simply put. So the opposite is true. If the data set is not normally distributed, then you can't apply it to a real life situation. It's that simple. You see, it's not difficult at all. Okay, so let's continue. So we test for normality. We test for normality of a distribution in order to know whether a specific hypothesis has to be run or not. I'm coming. Let me admit some of your friends in. Okay. So let me come back to what I was saying. I was saying that now we understand the two types of data sets that we can have. Knowing the two types of data sets that we can have, in order for us to be able to perform an analysis, we have to know whether that data set is normally distributed or not. Because we want to know if the hypothesis that we are generating from our data sets can be applied to real life situations. So we have to test to see if that data set we have is normally distributed or not, so that we can know what hypothesis test that we'll use to run. So we have normality tests, and then we have hypothesis testing. Very good. So moving on. Generally speaking, if the test is normal, then we run a parametric test. If the test is normal, then we run a parametric test. If the test is not normal, then we run a non-parametric test. Very, very simple. So if the test is normal, we run a parametric test. If the test is not normal, then we run a non-parametric test. Somebody might be asking, what test are we going to do or are we going to run in order to know if it is normal or not? So the test that we'll be using is called the homograph-Smirnov test or the Shapiro-Wilks test. The test that we'll be using is called the homograph-Smirnov test or the Shapiro-Wilks test. And then we will demonstrate how to run the homograph-Smirnov test or Shapiro-Wilks test in a few minutes. Okay. Please note that generally we consider a p-value of 0.05 when we are as the standard when we are running for tests. So we have to have a standard that will be able to compare our p-value to. Then we can stand on that and say that, oh, if we compare our value to the standard value, that is the 0.05, our test is normal or our test is not normal. So a p-value of 0.05 is the standard. Now, if the p-value is greater than 0.05, then it means that the test is normally distributed. If the p-value is greater than 0.05, then it means that the test is normally distributed. But if the p-value is less than 0.05, then it means that the test is not normally distributed. So we can also say that if the p-value is greater than 0.05, then the test is normally distributed. What does this mean? It means that the test is not significantly different from the normal, and then we accept the null hypothesis. So let me explain this statement. Before you begin any hypothesis testing, you first have to get your hypothesis. What do I mean by your hypothesis? Your hypothesis is your query. For example, the number of X-ray films in Ghana are not, your hypothesis might be that maybe government hospitals in Ghana have more repeated X-ray films than private hospitals. So you want to know if it is true or not. So maybe that can be your hypothesis for your project work in your final year. Maybe you want to know whether the number of X-ray films in government hospitals is repeated more than that of private hospitals. So your hypothesis is that it is more in government hospitals, and then your now hypothesis is that it is not more in government hospitals, but rather in private hospitals. So your null hypothesis will become what we generally know in the public. So generally, we can say that, or generally it is known that for government hospitals, they have more repeats. Maybe because the staffs are not well motivated like that of private hospitals. So they don't put in their all when they are doing they are not motivated when they are doing the X-rays. So you tend to have more repeated X-ray films, and that will cause more harm to the patient because more repeated X-ray films means more exposure. So that is what is generally known in the public. So it's just an assumption. So your alternate hypothesis will become that it is that general hypothesis is not true, but rather it's the private hospitals that do what? That have more repeated X-ray films. So in order for you to know if this hypothesis is true or not, you have to run a test for the hypothesis. But in order for you to know what test to run, you have to first run a normality test for that data that you have collected for your project to know if it is normally distributed or not. I hope you understand. So if it is normally distributed, then we know that the p-value is what? Greater than 0.05. But if it is not normally distributed, then we know that the p-value is what? Less than 0.05. Okay, moving on. So I would want to show you this. So this is a box plot, an image of a box plot, and it's showing the minimum and maximum values and then the median values with the different interquartile ranges. So please take note of this image. Then we have this here also that shows the skewness of a data. So if you have this going, the data distribution going this way, so you look at the tail of the plot. So if it is going this way, if the tail is pointing this way, then it is rightly skewed. If it is pointing this way, then it is less skewed. But if it is like this, then it is symmetrical. And then you can say the same for the box plots. If you draw a box plot and then you have this middle shifted to the left, then it is rightly skewed. If it's shifted to the right, then it is left skewed. If it's in the middle, then it is symmetrical. So please take note of this. And then we move on. Now, sometimes we can draw a plot that might look like this. So if the plot that you draw looks like figure A, then we say it is mesochaotic. Mesochaotic. If it looks like figure B, we say it is leptochaotic. Leptochaotic. And if it looks like figure C, then it's called platychaotic. 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 So this is another image showing platychaotic, mesochaotic, and leptochaotic plots as well.